Hello and welcome to this latest video for the Centre for Doctoral Training in Distributed Algorithms here at the University of Liverpool. My name's Dr. Peter Green. And today we're going to talk about samplers for Bayesian inference, where we're going to focus on an example application where we start with the example problem that has some kind of physical context and work through how you develop a Bayesian framework around it, and finish the video by highlighting why samplers can be useful in these scenarios. Okay, so while our previous videos have focused on sampling approaches like Markov chain Monte Carlo or sequential Monte Carlo samplers, in all of those videos we've talked about the idea that we're just trying to sample from some kind of probability distribution, which we call the target, which is usually written as a pi and as a function of theta in our notation. But we haven't spent too much time talking about what that target might be. And in fact, we've said that it can, for example, be Bayes' theorem. But what we've not investigated yet, and what we'll investigate in this video, is how you might take a real problem and phrase it in a Bayesian framework, such that you then go on to need one of these sampling approaches. So it's more dealing with the first part of phrasing your problem in a Bayesian way before you go on to using something like Markov Monte Carlo or sequential Monte Carlo samplers. So what I'm going to do today is I'm going to focus on an example that's kind of engineering related, because my background is as an engineer, and also it helps to give kind of context to how you might phrase these real life problems. So it's something that it's like a tangible problem. So what we're going to imagine is we have a problem where we've got this mass m, which can move sideways, and we measure its displacement with x. Now I'm going to join this mass to the wall on the left hand side with a spring. It has stiffness k and a damper. That's a damping coefficient c. So if you're not familiar with these things, a spring is a spring. The restoring force is proportional to the distance that the spring has been stretched. This damper is something that represents energy losses in the system. So if there was no damper, then this system could oscillate forever. And it's usually represented as a piston. So that's because if you think about dampers on cars, for example, they're often pistons which force oil through like a small gap. So that's what we use. So let's say we have this system and we've got some data. So let's say that a force F is applied to our system, and what we get is two time histories. So I'm going to draw that down here. So let's say that we're able to measure how the force changes with time. And let's say it's something non-standard. So it's not just a sine wave, for example. And then at the same time, we measure the response of the system, which in this case is its displacement x. So some force is applied to that mass and induces some kind of displacement. What we want to do is we want to estimate these two parameters. Specifically, we want to find k, the stiffness, and c, the damping coefficient. So there's lots of ways you can go about this, and as you can imagine, you can quite easily measure the stiffness of a spring just in a simple laboratory experiment, and you can measure damping as well in such a setting. But for now, for this kind of contextual problem, we'll pretend that's not the case. So perhaps this represents some kind of component that's currently in service, if you like, so we can't necessarily conduct tests on it. But we want to produce estimates of k and c, perhaps to see if the properties of this system has changed, maybe even to detect damage, that kind of thing. What we have is we have these two time series of data, x and f. So loosely speaking, you can imagine a good choice of k and c. So what we're trying to do is we want to infer these parameters from this data that we have down here. And a good choice of K and C is something that would make the response of this system, if we simulate it, look very similar to the response we can see down here. So the response of this system is governed by Newton's second law, basically. So F equals ma, in other words, mass times acceleration, so double dot represents acceleration here, is equal to the summation of the forces acting on this mass. So we have, if x is positive in the right direction, then using that picture we have this force F that's been applied to the mass. And we also have a restoring force from the spring acting in the other direction, and we get a restoring force from the damper as well, which is c times velocity. So this all comes from Newton's second law. Sometimes we can solve this for x, but it depends a bit on what the forcing function is. So for now, let's just say that we can simulate this system. We can simulate its response, and we usually do that with finite difference if you're interested. So if we say that we're going to simulate our system at discrete points from time is equal to 0 to time equals to capital T, then we'll say, okay, our displacement when we simulate it from time, let's say from time 0 to time capital T is equal to h. So I'm going to use h to represent our model. So that is the kind of finite difference simulation of this second order differential equation. Now h is a function of, well, we've got this time series of forcing, so I'm going to write that as a f from 0 to t. And then there's our two parameters as well. So we have to pick k, and we have to pick c. So like I say, you can imagine that at the most basic level, one thing you could do is you could just pick values of k and c, use this, simulate the response of your system, and you pick the k and c that gets you as close as possible to this true response that you have measured. So that's kind of the problem setting that we're going to work with. Okay, so to put that a bit more mathematically rigorously, what I'm going to do is introduce a bit of extra notation. So I'm going to write a hat of this particular x. That's just to differentiate it from the displacement signal that we simulate compared to the displacement signal that we actually measured. So if we were going to just pick the parameters that minimize the difference between our observed time history and measured time history, then one thing you might do is define some kind of cost function that you want to minimize. So let's call it j, which is going to be a function of k and c, as just being the squared difference between all of our data points. So let's say going from t equals 0 to capital T, what I mean is it's the squared difference between what we've observed, so each observation, which is a xt, minus the prediction made by the model, which now has a hat xt. Like I say, that's also a function of k and c squared. Okay, and then you've just got a simple kind of optimization problem where the aim is to find k and c that minimizes the cost function j, i.e. minimizes the square difference between what we've observed and what our model predicts. Alternatively, you might say, well, actually I want to be a bit more sophisticated than that. We'd like to quantify the uncertainty associated with our estimates of these two parameters. And we're going to investigate doing that with a Bayesian approach. So, okay, fine. We'll start off by writing down Bayes' theorem, and we'll just see what comes out. So, what we want to know is, well, what's the probability distribution over k, the stiffness, and c, the damping term, given the time history data that we've witnessed. So in that case, that is x from 0 to capital T. And you just write down Bayes' theorem. We know that that is going to be proportional to probability of witnessing that data, conditional on K and C, multiplied by probability of K and C. So as I'm sure we know already, this thing is called the likelihood, and this thing is called the prior. So we'll deal with the prior first. This is a problem where our parameters, stiffness and damping, have a physical interpretation. So let's just say that actually we can lean on our knowledge of the physics of the system to define a prior. And I won't write it down explicitly, but let's just say that for K, for a prior, usually stiffnesses aren't too bad actually. So let's just say we've put something like a Gaussian, and we think it's somewhere in this region. And for damping, let's say it's damping can't be less than 0, because then you start breaking laws of thermodynamics. So let's say we've got something like a gamma distribution that looks a little bit like this, something like that. So we've made some kind of choice based on our knowledge of the system. And in this case, we've also decided as a prior that the probability of K and C are independent. So probability of K and C is equal to probability of K multiplied by the probability of C. So it's just an example. You might choose something different, and it's kind of up to the user. Okay, so that's fine. The tricky bit, I think, is when it comes to defining the likelihood. It's not necessarily immediately clear what this really means. So it's the probability that you would witness this data given that you believed you have stiffness K and damping C. So what we're going to do is write down the most common expression that's used for the likelihood, and then we'll explain why. So we're going to say it's the probability that you witness X, time history from 0 to T, given stiffness and a certain damping. It's usually, well, often anyway, written as this product over all of our points of normal distributions. So that is xt is the argument, because we are looking at the probability of witnessing this data, so it has to be the argument of this distribution. And it has mean, the output of the model at that point, which depends on K and C. And then it's also got some kind of variance, sigma squared. So this is actually really important because we're making an awful lot of assumptions when we define the likelihood in this way. The key thing we're saying is that there's a probabilistic element, or there's uncertainty in our observations. So you can think of this as saying, well, if we truly believe in our model, that our model is a true representation of reality, then there's still uncertainty in what we will observe from that system. So that could be just because of measurement noise on your sensors, for example, but then it could also be because of other things, like the model in fact is not a perfect representation of reality. Perhaps there's friction in the system that we haven't considered, which, to be honest, is usually the case. So what we're saying is that if we imagine this time history of measurements, if the true time history is this, for example, then what we've observed is centered on this. So let's say this is the prediction made by the model. What we've observed is that, but it's been kind of corrupted with Gaussian noise. So what you actually see might look a bit like this. The other thing we've said is that it's the product of all these normal distributions. So what we're saying is that the uncertainty of witnessing, let's say, this point is not correlated to the uncertainty of witnessing this point, for example. And it might be true just if your sensors are subject to measurement noise from, electromagnetic radiation or something like that. But it's always worth questioning if that really is indeed the truth. Do you really believe that? So, for example, in this case, we're looking at the temporal case, but sometimes if you have, say, two sensors next to each other that are spatially very close on a structure, then the errors corrupting those observations might not necessarily be best treated as being independent. So there's quite a lot going on here, a lot of assumptions. The assumption that this noise can be modelled as a Gaussian as well is something you might have to question. So if you're interested, this is usually backed up by something called the central limit theorem, or sometimes the principle of maximum entropy, which we won't go into today. But the fact is that sometimes, it's just not true. So just as an example, which I'll draw over here in a different colour to show that it's different, sometimes you measure things like, something like number of faults that occur in a particular product, if you think about a manufacturing scenario. So if you have time on this horizontal axis and this is faults, then you have a sensor that can't report anything that's below zero. Basically, you can't have less than 0 faults. So if the true signal looks like this, and then what you observe might be a noisy version with spikes, that there will be spikes on this signal, but none of them will go below 0. And this is a case where, in fact, a Gaussian noise model perhaps isn't a very good choice. So it's something that you really do need to think about quite carefully. But we haven't yet talked about how we estimate this sigma squared. So if it is just measurement noise, then perhaps that's something that we already have a good estimate of. But again, it can include loads of other things, like the fact that the model is not a perfect representation of the physics that we are observing. So how do we estimate sigma squared, this variance term? In fact, what you can do is you can include it as another parameter to be estimated alongside, in this case, stiffness and damping. So we end up writing down our posterior such that we're saying, well, what we want is a probability of stiffness, damping, and sigma, given the data that we've realised. So how is that possible? Well, it's kind of easier to think about this in kind of loose terms with a few pictures when you think about how changing values of sigma changes the likelihood. So let's just say, for example, that we took our, let's say this is time, and we still have x here. So what I'm trying to represent here are our measurements. And I'm going to say that, let's say they look a bit like this. So what I'm trying to do is show that there's a clear kind of sinusoidal trend to our observations, but they've been corrupted with some noise, which obviously we can easily see as people, but the model can't necessarily. And we think about how the likelihood will behave when we try different parameters of k, c, and sigma. So if you try values of k and c, for example, that are not very close to what's really going on, and you get the general trend is completely different to the data, then you can imagine that the probability that you would witness this data, given that you believe the model should be, or the real system should be behaving like this, is very, very small. So essentially, all of these normal distributions, when you evaluate them, will end up being relatively small. So it is very improbable that you would witness this observation, given that your model says the observation should be this. So as you might imagine, a good choice of k and c will lead to your model's predictions kind of lying in the middle of the points like that. So what about sigma? Let's just imagine that k and c is fixed for the moment. If you chose to look at a value of sigma that was extremely high, then let's say these are 3 sigma confidence bounds. Let's say you chose a very large sigma. Then you might get something that looks like this. So like I say, this distance is 3 standard deviations. Then again, you'd say, well, if you really believed that your observations were corrupted by noise of standard deviation sigma, then again, it's very unlikely, it's very improbable that you would see these data points, these black points. You'd expect a larger spread. And so again, if you chose your sigma to be very, very large, then when you come to evaluate these product of these normal distributions, then again, they're going to be relatively small. And the same thing can happen if you decide to choose by accident sigma to be very, very small. If sigma is very small, then the confidence bounds might be a bit difficult to draw. But you can imagine what I'm trying to show here is they're very, very, very close to the mean prediction. And then, again, you would say, well, actually, if you believed that the observation noise was that small, then it is unlikely that you would have seen these black points. So again, those normal distributions in the likelihood will be relatively small. And because the posterior is likelihood times prior, then as you'd expect, if the likelihood is small, then the posterior probability is going to be small. So in fact, it would turn out eventually, and you can prove this, but I think we're okay doing it with pictures, that your best choice of sigma, i.e. the choice that will maximize the likelihood, will end up being something like this. Give you confidence bounds that nicely encompasses the data, 99.7% of the data, specifically for this Gaussian example. So what we're trying to do there is show pictorially how you can include sigma as another parameter to be inferred from the data, because we do learn about it from the data. In fact, what you're doing is by picking K and C, or searching for the best K and C and searching for the best sigma, you can think of it as by picking K and C, you're trying to pick this line in the center, and by picking the best sigma, you're trying to pick these confidence bounds. So we're going to go ahead and we're going to include sigma as a parameter to be found, to be estimated. So again, I'm going to write the likelihood. It's the probability of witnessing x from 0 to t given stiffness, damping, noise standard deviation. And then we've already got a prior over stiffness, a prior over damping, and now we're going to have to define a prior over sigma as well. And again, a little bit like with our damping constant, obviously noise variance can't be less than 0, so you might choose something like a gamma distribution. So we've rewritten Bayes' theorem now to include sigma, but this likelihood term is still the same. So this is still equal to this. All we're saying is that now sigma is an additional parameter to be inferred. Okay, so to write this a bit more compactly, let's just say that theta, to refer back to our previous notation, is all the parameters we want to find, which is stiffness, damping, but now includes sigma. And what we've got is the posterior probability of theta, given our capital T data points, is proportional to the likelihood, which we've defined already, and is the product of lots of Gaussians in this case, multiplied by a prior, which we have defined as being a product of 3 distributions. That is the prior over the stiffness, damping, and noise standard deviation. So if you want to propose a vector theta parameters and evaluate its posterior probability, to kind of draw that out, what you do is you go from your theta. From there, you conduct a simulation. So using the notation we had before, that gives you, the output from the model, which had a kind of hat on the top from 0 to t. And that was equal to, again, using our previous notation, our model was written as an h. And depending on the force from 0 to t, as well as the stiffness and the damping terms, which are in theta. Once you've got that, then you can go on to evaluate the likelihood, where that's where you use your value of sigma, the noise standard deviation. And likewise, let's say on a sort of different path with your thetas, you can immediately evaluate the prior as well. So then you've got these two things, multiply them together, and then you've got the posterior probability of that particular parameter vector. So it almost sounds like the problem's finished. One of the things you might do is you might then choose different values of k, c, and sigma to investigate, and you might investigate those over a grid, for example. So I'll draw this in 2 dimensions just so we can visualize it. So we'll ignore sigma for now. Let's say you might try different values of k and c across this grid. And then what you'll end up with is a kind of idea of the shape of the posterior probability distribution over this grid. So I should say that specifically in this case, we're dealing with a scenario where we don't have a closed form solution for the posterior distribution. And that's because we have this, well, one of the reasons could be because we have this model that doesn't actually have a closed form solution inside it. So, okay, we might be able to evaluate parameters, including sigma, over some kind of grid, and then we can get an idea of what the posterior probability distribution looks like, but this doesn't necessarily help us very much. So a problem with this kind of approach is, well, imagine if you've had lots and lots of parameters, then the dimension of this grid that you have to explore will grow prohibitively, so something that's called the cursive dimensionality. And also, ultimately, just knowing what the posterior distribution looks like isn't necessarily the most useful thing you could want to know. And if anything, what we really need are samples from the posterior distribution. Why do we need samples? Well, so let's imagine if we're able to get some samples. This is usually a superscript. So let's say we've got 0 to n samples generated somehow from the posterior distribution, then is in probability of theta given x from 0 to t. Obviously, we can use these samples to calculate statistical moments that relate to the posterior, so mean, variance, etc. But also, you might need those samples if you want to come and make predictions. So let's say that a new force arrives to our system, which I'm going to write as an F star. So there's a new kind of force, and we're going to use our model to predict how the system is going to behave when it's subject to this new forcing. So it's the displacement response. I'm going to write that as an X star. So that's the response. And we want to predict X star given F star, but also we want to factor in the uncertainty we have in our parameter estimates. So usually what you do is you would write down, well, what we want to know is the probability of X star, probability of witnessing that response to force F star, but also given that we've seen all this previous data as well. And what you can do to kind of factor in your parameter uncertainty is, so you can see the parameters aren't included here, is we integrate over them. So we say, well, that's the probability that you would witness X star given F star and theta. So notice that I'm saying it's the probability that you would witness this. So again, this is just the likelihood again. This will just be a normal distribution. centered on the response of the model because of the way we chose the likelihood earlier when we were defining our sort of Bayesian framework. And you'd multiply this by the posterior probability of theta given x0 to t. And you integrate over theta. So you're essentially marginalizing over theta. So you're propagating the uncertainty in your theta estimates into your predictions. If you're very lucky, you might be able to calculate this in closed form. But often that's not the case. If you have samples from the posterior distribution, then what you can do is you can say, well, this is approximately equal to, and it's like a Monte Carlo estimate. So it's a 1 over, okay, I've gone from 0 to n here, so we've got an n plus 1 samples in this case. Summation from I is equal to 0 to n. And then this is our probability of witnessing x star given f star and the, let's say, sample I, where what we're saying is that sample I has come from the posterior distribution. So that's another example just trying to illustrate why it's useful to have these samples. And what you need is some kind of algorithm that is able to generate these samples from some kind of generic probability distribution. So we're able to evaluate this at any point, but that doesn't necessarily mean that we have a way of, it can still be a non-standard probability distribution, is essentially what I'm saying. So you need some kind of algorithm that's able to generate these samples for you. And that is where we do things like we use Markov chain, Monte Carlo, or as we discussed in previous videos, sequential Monte Carlo samplers, is to get those samples. Okay, so hopefully that's been useful. Just to recap, we've picked a problem with kind of physical meaning and context, where we're trying to identify a stiffness term and a damping term from a time history of displacement measurements. And we've kind of walked through how you might decide upon a prior, how you might decide upon a likelihood, and the implications of your choices. And we've also described how you can include in this case, sigma, which we described as essentially it's the likelihood standard deviation, as a parameter to be identified alongside the physical parameters, i.e. stiffness and damping, that we were already interested in. And we've shown that what you can end up with is you have a probability distribution that you can evaluate at any point. So you can put a theta in and you get its posterior probability out, but that distribution could well be non-standard. If you want to generate samples from it, which are useful for a number of reasons, then you would need something like Markov chain Monte Carlo or sequential Monte Carlo samplers.